Hello and welcome back to the sixth part of the tutorial on writing your own operating system. So where were we in the last video? So if this is your processor, and here's your programmable interrupt controller. And this is connected to, for example, the keyboard, also the mouse, and also the hardware clock. So what we did last time is we established the connection between the CPU and the programmable interrupt controller, and we actually received the first interrupt from the clock. So this is a good thing. So this means that we actually have a connection now. But we had a problem that after we got this interrupt, the system just stopped, and that's not what it is supposed to do. You know, it's actually supposed to get the next timer interrupt, the next timer interrupt, and we have a problem that we didn't answer the interrupt. So we didn't tell the programmable interrupt controller, okay, done. I have received this, and it's okay. You can continue with whatever you were doing before. And we will do this in this video now, and then we can actually really start to get a decent communication with the keyboard. Okay. So the problem that we have now is if this is your C++ world. So here we have our kernel main, and we build this object with the global descriptor table and the interrupt manager, and we connect these in our objects in a way. And now an interrupt occurs, and the interrupt kicks us out of this C++ world into something like an assembler world, right? So that's why we wrote the assembler code, which did all this hard stuff just to get back into the C++ world. But so far we only went into a static function, right? So and that's not really what we want, right? And we are writing this in C++ because we want to have the power of object orientation. So we really want to get back from the static function back into this object-oriented construct, right? So and actually, to answer the interrupt to the PIC, we have to send data back through the command and data ports, and the command ports and data ports, they are actually members of this interrupt manager, right? So these are members of the interrupt manager, so we actually have to get from this static function into a method of the interrupt manager just to have access to the connection to the PIC. Okay, and I'm actually not a big fan of this. So what we'll do is we will have a static pointer to the interrupt manager. I'm not a big fan of having static pointers to things, and but I think really we don't have much of an option right now because we are in a static environment at this point, and in a static environment we only have access to the static object, so we need to have a pointer to the interrupt manager in a static variable. As I said, not a really great design, but I don't think we have much of an option So what I'll do now is in here, in the interrupts.h, I will put a pointer to the current interrupt manager. So we only can have one active interrupt manager. Okay, so now then we have this, and our handle interrupt function will then call the non-static method doHandleInterrupt of that interrupt manager object here. Okay. So in the interrupts.cpp, yeah, we need to have. I mean, this is a static object, so we must put the initialization here. Initialized with 0, and then here in the activate method, we will just set this to this pointer. But I mean, in theory, we could have multiple interrupt managers. I mean, but that doesn't actually make sense, right? Because the processor has only one interrupt descriptor table, and so there can be only one active interrupt manager at a time. So, but I'll put this here. If the interrupt manager has already been set, then we will deactivate the old one and then set the new one. Okay. And deactivate so if we are calling deactivate on the active interrupt manager, then it is supposed to deactivate it, and if we are calling it on a different object, then it is already inactive. So then we don't have to do anything. So okay, so yes. Okay. Now in the handle interrupt, we can now, we can now use this pointer and call doHandleInterrupt on it. And the doHandleInterrupt will basically be the same thing, just on an object. So So we'll just pass the parameters and return what we get back from that object. And otherwise we'll just return the original ESP. Okay? So now let's have this do handle interrupt method. And so here we put the stuff that we really do now. So let's see. So this should behave the same way it behaved before. Okay, so what we've seen now is, the operating system does the same thing as before now, but in a different way. So what we did now is we jumped from this static function back into the interrupt manager object, and there we have access to the PIC connection. Okay. What we can do now is, at this point in this do handle interrupt method, we can now actually send the answer to the interrupt, and then the program, the operating system will not halt here. So. Let's see. So in this method, okay. We only have to send answers to the hardware interrupts. So we have to, which are the hardware interrupts? We have remapped the hardware interrupts from the PIC to 0x20 to 0x30. So So in this case, we have to send an answer. So this is the answer that the pick wants. And if we are also, so this is the answer for the master pick, and maybe we also have to send an answer to the slave, but not always. So the same answer, but only if this was actually an interrupt that came from the slave. So only if the interrupt number has been between 0x28 and 0x30. Okay, now let's see what happens now. And you see now we get lots of interrupts. So this is really a good thing. So let's stop this. Yeah, I'm really happy right now. So so this works kind of already, and I mean we don't want to have this output every time we get a timer interrupt, right? So so I would say that this output should only be there if we are not, if the interrupt is not the timer interrupt. And the timer interrupt is the interrupt 20. So so if we run this now, then we don't get this output because yeah, we still get the interrupts, but we don't print them on the screen all the time because they are really not that interesting, right? So yeah. So now we get all the interrupts. What do we do next? Well, I mean, we are programming this in C++, right? So we want to use object orientation, and the object-oriented way of proceeding now would be to have objects for the different interrupts, right? So and then so for example, for interrupt 0x21, which is a keyboard interrupt, we would want something like a keyboard driver or something which handles that interrupt, right? So so we need to define some interface for these keyboard drivers, mouse drivers, and so on, which the interrupt manager can then use. Okay. So so what I'll do now is I'll have another base class called interrupt handler. And this so the base class will basically just know its own interrupt number. So and a pointer to the interrupt manager that it is connected to. Okay, and I want to make the constructor and destructor protected so that you cannot instantiate this. You know, we don't have purely virtual functions, and so we cannot have abstract classes. So I'll just handle it in the way that by making the constructor protected. So. Okay, so this should work. And we will also make this new class a friend of the interrupt manager. Okay, and now we will have basically something like the interrupt descriptor table, but on a higher level. So here we will have an array of interrupt handlers. Like this. Okay, so now we'll have to implement these methods. Okay, so the constructor will just store the values you give it. And then it will put itself into this array of the interrupt manager. And in the destructor, it will unregister itself. Okay, like this. And the standard behavior for handle interrupt is just returning ESP again. Okay, now in the constructor of the interrupt manager, we also have to set the handlers to 0. Like this. And then down here we can proceed and say if handlers so if we have a handler for it, then we call its handle interrupt method. Giving it the stack pointer. Okay. Okay, and then we can print this message about an interrupt that we couldn't do anything with, only in the else case here. So if we have an interrupt handler, then we use that. Otherwise, we'll print this message. So this will also tell us the number of the interrupt that we didn't handle. Okay, this looks good. Okay. So some object file wasn't updated, and so just make clean and make run fixed the error. So okay, so now the interrupts work as we want them to. Now the next thing we can do is we can write a driver for the keyboard, and because if we just activated the keyboard and you press a key, then the PIC will send the interrupt. The CPU will tell the PIC, okay, I'm done with the interrupt. The problem is that the kernel would still stop. It would not continue running because the PIC would not accept the answer from the CPU. The reason is if you get a keyboard input, then the PIC demands that the CPU fetches that input before it tells the PIC, okay, I'm done. So that's what we will do next. We will make a driver class for the keyboard. It will be derived from the interrupt handler, and it will have its own ports. And then we will just activate it, and if the interrupt comes, it will read from the data port, and then we will have an actual hardware response. Okay? So let's do this. Okay, keyboard.h, the usual stuff. Okay, so this class needs 2 ports, and this is really a relatively normal design, which we will see very often in the future. So we will have just 2 ports, a data port and a command port. Wait, did I do this correctly? Oh, this seems to work. Of course. Okay. So in this keyboard CPP, we'll have to do a little bit in the constructor. So the interrupt handler is first. So the interrupt handler is for the interrupt 0x21. That's the keyboard interrupt. And we just pass the manager object to the base constructor. Then we construct the data port, which is port 0x60, and the command port, which is port 0x64. Okay. So down here, if we know there is a keystrike, then we have to fetch it. Like this. And I'll just copy this over here. Okay, so this will print the key, and we need to have the forward declaration for printf. So that it accepts calling printf. Okay. Now, in the constructor, so this, when we start communication with the hardware, we will just wait for, I mean, if you start your operating system and you hold down some key, why ever, this will just wait for you to stop pressing that key, and it will just remove all the keystrikes that might have been there before. So, so this command tells the PIC to start sending keyboard interrupts, I think. Or maybe it tells the keyboard to communicate using interrupts. I'm not really sure. After that, we send it the command 20, which means give us your current state. And then we read that. And then we set the leftmost bit to 1 because this will be the new state. And we will also clear the 5th bit. Like this. Okay. So then we write command 60, which tells the pick or the keyboard to change the current state. So you see, we set command 0x20, which gives us the current state. Then we change to the current state and write it back. So and I think this finally really activates the keyboard. Oh, I almost forgot. We need to put this, of course, also here. And in the kernel, we have to include the header. And instantiate the object. And notice this, we instantiate it between the instantiation of the interrupt manager and the activation of the interrupt manager. And it gets a pointer to the interrupt manager. Like this. Okay, so this should work now. Okay. It didn't do anything. Okay, so now we have an interrupt from the keyboard, 0xFA. I think this basically says, okay, I'm fine with, I'm done doing whatever I need to do, so I'm ready now. I think this is what that means. Now, when you press keys, the first times you press a key, you will get this this keyboard key code 0x45 and 0xC5, and I think that's the key code for the numlock, and I think this is what VirtualBox does to tell the virtual machine the state of the numlock. So I think we can really ignore them. And yeah, I think this FA is really a status interrupt, so we could ignore that also. So we could put some if statements here which say, okay, for 0x45 and 0xc5 we don't do this. Well, let's, in a better way, let's say switch the key. And this is just the default behavior. And for 0x45, we just do nothing. And also for this 0xfa. Okay, now when you press a key, I just pressed the A key, and you see we get two interrupts. So the first one, when I press it, and if I keep holding it, I get the same interrupt over and over again. And when I stop pressing, then I get basically the same interrupt, but the first, the first bit of this 8-bit integer is just 1 for key release and 0 for key press. Okay, so you will get the same key code twice. You know, one when you press the key and again when you release the key, just with a different first bit. So. So maybe we'll just ignore key codes. So everything after 0x80 are the key release interrupts, and we are at this point we are not that much interested in it. So I press A, B, C, D, and you will realize the key codes that you get, they are terrible. I tell you, they are terrible. They are all over the place. So you will not really have an option. You will just have to take a sheet of paper and press every single key and see which key code do you get and write that down. And then for every single key, you will have to make your own case here. And that's really crazy. I tell you this. But let's see, just as an example, I'll just put case 0x1e. And in that case, I'll printf the letter A. Because that's the key code on this keyboard. The worst thing of this, the worst part of this is on different keyboards, the same key codes will have different meanings. So here, if I press Z, I get 0x15, and on American keyboards, 0x15 is a Y. And this is stuff that you probably remember from back in the days when you remember the DOS programming. This is stuff you had to deal with back in these days, right? But so now I've compiled this again, executed it again, and now I press A, and you get an A. Great, isn't it? So so now we finally get real data from the hardware. You know, if I press A again, I get more A's. And then what you would do next now is just fill in all the cases with all the other keyboard key codes, and yeah, maybe you just copy and paste the thing from my zip file, but whatever. So this is really a bit tedious, and I'm not going to put this in this video now. So so this should be enough for today. I think we have really achieved something, a milestone now, because now we really get data from the hardware. We press a key, the key A, and we put an A on the screen. And this is really a great feeling, I think. One thing I want to tell you, at this point, at least when I came to this point for the first time, I thought, hey, this is great. I want to run this on the actual hardware. And I said make install and reboot it. And I pressed the key and nothing happened. And that was really frustrating for me. And it took me quite a while to figure out what the problem was. So the problem was this is a USB connection. So I mean, VirtualBox will communicate with your operating system and pretend there is a PIC, but on your actual hardware, a USB keyboard isn't actually connected to a PIC. Okay, I think it is connected to a PIC, but not like this. This would be, I think, the PS2 connections would be directly connected, but now you have on actual hardware you have your USB ports, and then you have your mouse there and your keyboard there. And with this scenario you cannot. So this scenario you cannot handle right now. So, but my computer at home had. Luckily, it had a BIOS setting. I think it was called Legacy Operating Support or something like that. And when I enabled this setting, the motherboard really did all the USB stuff and then emulated the behavior with the PIC and the keyboard and mouse like this. And when I enabled this BIOS setting, then I could actually press keys and get them on the screen. So if you have a setup like this, then either you have to stick with VirtualBox for now, or maybe you have such a setting like this, and otherwise you will get to run your stuff on actual hardware only when we are at the point where we can communicate with USB. Okay, so this should be enough for today. Tune in next time. Next time we will talk about the mouse. But let me tell you now that we have all the stuff with the interrupts and the global descriptor table and everything. The mouse is really easy. So the mouse is really quite similar to the keyboard. And you've seen once we had all the interrupt stuff running, we came to the point where we could actually use the keyboard relatively quickly. And we'll get to the point where we can use the mouse relatively quickly now also. Because the really tedious stuff, the interrupt descriptor table, all the assembler codes, the boot manager, the bootloader stuff, the global descriptor table, all this hard stuff is now over. We are now finally at a point where we can really do stuff, right? All this necessary but tedious fundamental stuff is over now, and now we can really get going and do stuff. Okay, so yeah, see you next time, and don't forget to subscribe so that you don't miss the next video. See you next time.